Let's take a few moments to go over 4 kinds of electrochemical cell problems. These are galvanic cells, not electrolytic cells. So these run by themselves. First, we find standard electrochemical cell potentials by subtracting the half cell potential at the anode from the half cell potential at the cathode. We get this information from tables such as the one you see on the screen here. Let's pull that down a little bit. And you can see that for the zinc 2 plus, which is written as an oxidation, we have a reduction potential down here of minus 0.76 volts. When we subtract the anode from the cathode potential, we're always going to use the reduction potential, not the oxidation potential. And we can see also that the copper 2 plus to copper is a reduction, and that's going to be 0.34 volts positive. If we use the formula we see at the top of the page, what we end up doing is adding 0.76 to 0.34 because we're subtracting a negative number, and we get 1.10 volts as the full cell potential. The second type of problem that we would want to do is finding a non-standard electrochemical cell potential. And here we use the Nernst equation. The potential of a cell is equal to the standard cell potential measured at 25 degrees Celsius, 1 atmosphere pressure for gases, 1 molar solutions, minus R times the absolute temperature divided by N times F, and we'll talk about Faraday's constant in a moment, times the ln of Q, where Q, of course, is derived from the net ionic equation. That's the product of products whose concentration can change, that's the zinc 2 plus in this case, divided by the product of reactants. Q here then is simply the zinc concentration divided by the copper concentration when we start the reaction. And we've set that at 0.10 for the molarity of the zinc ions and 0.20 for the molarity of the copper ions. Now, when we then use these numbers in the Nernst equation, we take the 1.10 volts that we worked on and found in the previous slide, and we're going to subtract RT over NF times the natural log of Q. Now what I'd like you to do on your calculator then is to find, just type in 0.5 because that's Q here, 0.1 over 0.2. Push 0.5 into your calculator and take the natural log of that. Then multiply that number, which is a negative number, by 8.31, divide it by 2, that's the moles of electrons in the net ionic equation. We go from 0 to plus 2, from plus 2 to 0. Multiply by 298 K, because that's the standard conditions that we use for the standard cell. And then you're going to divide by 96,500 coulombs per mole. That's called Faraday's constant, and that will come up again and again in our electrochemical work. When you do this, you will find that this whole expression is equal to about minus 0.01 volts. And when we subtract a negative 0.01 volts from 1.10, the negatives cancel out. We simply add the 0.01 volts and we get 1.11 volts. So by having the concentration of the zinc here, we find out that we just add 1/100 of a volt, 1%, to the voltage of the standard cell. And of course, the more we reduce the zinc 2 plus concentration, the more the reaction will go to the right. That's something that Le Chatelier would predict. And therefore, the higher will be the cell voltage. If we did the same thing, if we increased the zinc concentration or reduced the copper 2 plus concentration, we'd be pushing the reaction towards the left, and that of course would reduce the cell voltage. The next skill is to find delta G, that tells us whether a reaction will go or not, from the standard cell potential. And we use the equation delta G equals minus N times F times the E0 standard voltage of the standard cell. And if we use the aluminum-bromine reaction, we can see that if we separate this into half reactions, we end up giving away 6 electrons from the aluminum and taking in 6 electrons to the bromine liquid. If we then look up the half cell potentials, for the aluminum it's minus 1.68 volts, for the bromine it's plus 1.06 volts. We subtract this from that and we get a cell voltage of 2.74 volts on the standard. We can then plug that into this equation and we calculate delta G, negative, that's in the equation, 6 moles of electrons times, now we're going to use a more accurate Faraday's constant, 96,458 coulombs per mole, and we multiply by the 2.74 volts of the standard cell potential. When you do that, you get 1590 followed by 3 zeros joules, which is minus 1590 kilojoules. The negative sign comes in here. Delta G then is a negative number, and that of course means that this reaction will proceed without any additional help from left to right and proceed pretty dramatically. That's a lot of kilojoules to get out of this reaction. So this is favored to go left to right. Now how about finding K from a standard cell potential? Well, we use this equation, E0 of the cell equals RT over NF times the natural log of K. This is like the one you did before, but now we're looking for the equilibrium constant. So to find K for this reaction, and if you're familiar at all with metals reacting with acids, you can see that copper is not a metal that reacts with, say, hydrochloric acid. You need concentrated nitric acid to react with copper. So we shouldn't have much of this going on. There shouldn't be much copper 2+ and hydrogen gas produced out of this combination, and the equilibrium constant then should be much, much less than 1. Well, let's look at that. Well, we write the balanced half reaction so that we can find the number of moles of electrons transferred, and since we're going from copper to copper 2+, that loses 2 moles of electrons per mole of copper, and then is equal to 2. We can then look for the E0 of the cell, and if we just look up the copper and the hydrogen, we can see that that's a negative 0.34. That is a giveaway here, because if a cell voltage is negative, that means it won't go in the direction that it's constructed. The voltmeter will not move forward, it'll move backwards, because the natural tendency of this cell is to move from the copper 2+ and hydrogen to the left to make copper metal and hydrogen ions. Now I'm going to let you do the math to solve this equation for K, but if you do, you will see that K is equal to E raised to this power. Here's your voltage, here's your 2 electrons, and when again you do the mathematics up top, you will see that at 298 Kelvin, that R, T, and F are represented by this number, 0.025693. And when you raise E to the power that's represented by this expression, you see that it's 3.19 times 10 to the negative 12th. That's a very, very small equilibrium constant. That means almost none of the reaction ends up as copper 2+ and hydrogen gas. So our question then is, for this reaction, is delta G less than, equal to, or greater than 0? And if you think about it for a while, you realize that with an equilibrium constant this small, this reaction is not favored, and therefore delta G cannot be less than 0. It must be considerably greater than 0. So that's how you do those 4 problem types.